You know, what does a simple high five have in common with a massive rocket blasting off into space? Well, it turns out they're both run by the exact same incredibly powerful rule. Today, we're going to pull back the curtain on the unseen force that shapes pretty much every single interaction in our universe, Newton's third law. Our story starts with a scene you've probably seen 100 times, maybe even in a physics textbook. But just ignore the text for a second and look at the picture. Two friends on skateboards. One pushes off the other, and right away, we have a puzzle. Why do they both move? I mean, it looks like only one person is actually doing the pushing, doesn't it? Well, the answer to that question reveals a fundamental secret about how our entire world works. To solve that little skateboard mystery, we've got to start with what I like to call the everyday push. Because really, the amazing physics behind that moment begins with a very, very simple interaction. And here it is, the big one, in Isaac Newton's own famous words. For every action, there is an equal and opposite reaction. Now, that single sentence is a massive cornerstone of physics. And it sounds pretty straightforward, right? But unpacking what it really means, well, that's where we find the secret to motion itself. So, that brings us to what we call the action-reaction law. This is where we're going to really break down the forces at play and get to the bottom of what action and reaction actually are. You can actually see this law perfectly with a super simple experiment. Just imagine blowing up a balloon, taping it to a straw that's on a string. The second you unclip it, air rushes out the back. That, right there, is the action. And the reaction, the balloon zips forward along the string. So you see, the balloon pushes the air, and at the exact same time, the air pushes the balloon. Okay, but wait a second. This leads to a question that honestly trips up a lot of people. If the forces are equal and they're opposite, shouldn't they just cancel each other out? I mean, why would anything move at all? It's a fantastic question, and the answer? Well, the answer is the key to this whole thing. And here's the crucial aha moment. The forces don't act on the same object. Think about it. When a tennis racket hits a ball, the racket puts a force on the ball. That's the action. But at that very same instant, the ball puts an equal and opposite force back on the racket. That's the reaction. They're an inseparable pair, but because they're acting on two different things, the ball and the racket, they can't possibly cancel out. And here's the real kicker. While the forces are equal, their effects are totally different. Thanks to Newton's second law, the ball's tiny mass means it goes flying, while the much heavier racket and player barely move. You can see it perfectly right here. One force acts on the ball, sending it soaring across the court. The other force acts on the racket, which the player feels as that thwack of impact. They can't cancel out because they aren't fighting over the same object. That is the secret. Okay, so now let's take this idea and apply it to something a little more dynamic. Collisions. It turns out Newton's third law is the absolute master rule for what happens when any two things slam into each other. So, first up, we have something called an elastic collision. The easiest way to think about this is as a clean collision. Picture two billiard balls. They smack into each other, they bounce off, and basically no energy of motion, that's kinetic energy, is lost in the process. It's a perfect rebound. Then you've got the other kind, the inelastic collision. This is where things get a bit messy. The objects collide, but instead of bouncing off, they kind of stick together. In this case, some of that energy of motion gets turned into other things, like the sound of the crash or a little bit of heat. All right, now let's look at them side by side. On the left, in the elastic one, see how the moving object just stops and the one that was sitting still takes off with the same speed? It's like a perfect handoff of energy. But now look at the right, the inelastic collision. They smack into each other, they stick, and then they move off together with a totally new speed. Two very different results, but both are perfectly governed by those same action-reaction forces. So we've seen this law in simple pushes, and we've seen it in collisions. But what about using it to do something truly spectacular? In this next section, Taking Flight, we're going to see how action-reaction literally lets us defy gravity. I mean, just check this out. A flyboard looks like straight-up magic, doesn't it? But it's just pure physics. The action is that incredibly powerful jet of water being forced downward. And the equal and opposite reaction? Well, that's the force that shoves the rider straight up into the air. It's that direct and that awesome. And believe it or not, it is the exact same principle that powers a drone. The action is its propellers shoving a whole bunch of air down. The reaction, the air pushes back up on those propellers, creating lift. It's really that simple. Push air down, and you go up. It's Newton's third law flying around in your backyard. And all of this brings us to our final big takeaway. Starting to recognize this unseen force working literally all around you all the time.
So if there's one thing to remember from all this, it's this. From that simple push on a skateboard we started with, all the way to the roar of a rocket engine, every single force is just one half of a pair. Nothing pushes without getting pushed back. It is a constant, invisible dance happening everywhere all at once.
And that kind of leaves us with one last thought. Just look around you for a second, right now. As you're sitting in your chair, as your feet press against the floor, as you're holding your phone, what unseen action-reaction pairs are shaping your world in this very moment?